right, thank you for that introduction, Julie, and thank you to everyone who joined the webinar today. And I'll start right away with an agenda. Here is the agenda for this session. We'll start with a quick overview of the gap that we see in the IoT market today. I'll introduce you to the SaaS solution for IoT. We will look at a demonstration of SaaS analytics for IoT and finish off with one of our customer stories. So let's get started. IoT is often primarily perceived as the process of connecting to devices and collecting data. But what customers are realizing is that without applying AI or any type of analytics to that data, they struggle to deliver value from their IoT initiative. The opportunity space is wide, and we've been working on a number of customer initiatives in smart manufacturing around improving production quality and maximizing equipment performance, which includes predictive maintenance, in smart energy and utilities around forecasting energy demand and increasing grid reliability, in smart retail, providing real-time customer engagement, and also smart cities, smart transportation systems, usage-based insurance, and also smart healthcare, for example, remote patient monitoring. So what does the market need, and background to why we built this product? What we've been hearing from customers in the industries I mentioned before is that there are several barriers to IoT projects. The first is a set of challenges related to the IoT data itself. In order to achieve meaningful business outcomes, multiple disparate data sources need to come together. Machine and sensor data without enterprise contextual data about the machines, the environment, and the history they operate in often results in not generating valuable and actionable business insights. Data is often locked in fragmented PLCs, SCADAs, controllers, MES or ERP or APM systems or other systems. Raw sensor data can also be patchy, unreliable, anomalous, missing or not synchronized in terms of periodicity, all things that negatively impact analytical performance. It's also very challenging to present all the dimensions and aspects of a digital asset to an analytical platform. And this includes the hierarchies and relationships, just to name a few. All these data challenges often leave projects stuck in their ETL or data lake stage, and they fail to mature to deliver business value. The second set of challenges involves the complexity of performing the analytics and creating execution systems for it. Data scientists are a scarce resource. They rarely exist in the manufacturing industry, and engineers are rarely equipped with the same skill set to be able to code themselves complex analytical systems. The analytical life cycle is very hard to scale and manage in any industry, as well as executing AI in stream, especially in those industries that have not done that in the past, which is often the case in the industrial sector. So SaaS analytics for IoT is a proven way for business users to organize and act on high volumes of diverse IoT data using a secure, flexible, and scalable IoT analytics solution. It's not a new product. It's a product that has been on the market for a while now, and we've just launched version 7.1. It's our latest version of this product. And what it does, it provides a single version of the data for a wide variety of users across the organization, enabling non-technical users to quickly extract value from IoT investments in days, not in months. So really accelerating the time to value. What we wanted to achieve with analytics for IoT is to access data of any complexity, size, speed, format, or source. We wanted to automate the data preparation with an out-of-the-box data model that is ready to go and abstract any ETL or underlying schema complexities away from the business user. It provides access to the best AI and machine learning algorithms available in a drag-and-drop visual interface, as well as it enables open APIs so that popular Python libraries and open frameworks can be used in the process as well. And then have an easy method of deploying, executing, and monitoring models in production. In our demo today, what I'll show you is how the entire IoT analytics lifecycle can be performed from one solution by non-technical users, from connecting to field, machine, sensor data, and also enterprise contextual data, all within the structure of the digital asset, selecting and transforming relevant data for the purpose of performing an analysis and building a model, exploring and understanding relationships in the data, building, training, and testing analytical models, deploying them to data in motion, and managing models over time. And then take action and integrate back with the operational systems. Just before I kick off the demo, I would just like to take a few minutes to explain the high-level logical architecture of analytics for IoT. On the right-hand side, you can see we have the environment in which analytics for IoT operates. This can be on-premise, as is often the case in manufacturing. It could also be an off-premise data center, and it could be on the SaaS cloud or on the public cloud, Google, AWS, or Azure. The core of analytics for IoT is the SaaS VIA platform. It's the ability to perform the analytics lifecycle end-to-end. This is underpinned by an extensible industrial data model that we built. It's a data model that can represent an entire asset, for example, a factory, as in our example today, with its production lines, machines, process data, maintenance data, fault history, the product, the material data, supply chain data, and sensor data. It also has built-in ETL, extract, transform, load functionality to easily connect to source systems, and provides business users or engineers a data portal where they can mash up these data sources into a visual analysis that will feed into the analytics lifecycle. Sensor data can be captured over a network message broker or an IoT platform that connects a message gateway to the source sensor data. A common deployment pattern is for a field data aggregator to serve as an IoT gateway to the sensors and controllers on one hand, and communicate the factory sensor data on the other hand to the cloud or data center for storage. SAS Event Stream Processing, or ESP, is our high-velocity, high-throughput streaming engine. We use it to both ingest data in motion as well as implement and execute the models built in the analytics lifecycle and have the data streaming through those models in real time. ESP execution can happen in several places at the same time, both in the cloud or data center, as well as back in the factory on the IoT gateway itself, where the data is being collected. Any AI model built and trained in the cloud can execute on the edge. It could actuate and deliver value even if the factory remains completely disconnected from the network. As part of the analytics lifecycle, model performance results and analytical outputs can be used to monitor the model performance over time and retrain the model. A new model can then be updated and published easily and at scale by the event stream manager back to the edge, either directly over the network or through an IoT platform device management capability. So I'm now switching over to our demo environment. And you should be seeing a number of steps here in the menu. You should be seeing steps that correspond to what I described as the analytics lifecycle. And what I'll start with is a very top-line report with several key performance indicators. So this is a full HTML5 drag-and-drop BI environment where this manufacturing company built themselves this dashboard. This manufacturing business spans across several different regions. And in my next tab, I could actually see some production indicators. So here I can see some indicators around yield, yield by month grouped by product name, and cost and value of quality for different facilities. One of these facilities, which I'm highlighting, is the Portland facility, and the cost of quality, value and cost of quality is unusually high. So I can see that it's mostly impacted by a declining yield in the Portland facility, and I can also see that more specifically, the yield of product number 4 has declined in the Portland factory. So this has given me some high-level overview on an area that I would like to research. And what I'll do next is I'll contact the quality manager of the Portland plant to kick off an investigation using the plant data. This is where I go into analysis of IoT data. So as a plant quality manager or quality analyst, I'm using analytics for IoT. This is an environment that allows me to quickly ingest the entire plant data. And while we do this, I'll open up a Portland product number 4 investigation. All the tags or sensors that I have installed across my shop floor in all the different machines is here, and also my plant contextual data such as maintenance data, production data, all within the logical hierarchical structure of my assets. Sometimes this is referred to as a digital twin. Essentially what I have is all the dimensions relating to my manufacturing process and associated data from my enterprise systems. This industrial data model, which can represent my entire digital asset, along with the ETL behind it, that populates and ingests this data, this comes out of the box with the product, with analytics for IoT. We've seen over the last 10 years in these types of industrial projects that just getting to a single integrating version of the truth of a production process, this normally takes a very long time and a big effort. So I think we've overcome this with the automation we built into this. That's a big accelerator to value. And also the fact that Analytics for IoT offers me, as a plant quality manager, not only the sensor time series data, which on its own in isolation may not be able to help me run my investigation, it also allows me to pull up right away the sensor data enriched with product, maintenance, production data all together, which is a very big accelerator. So as the quality manager for the Portland plant, I really don't need to know anything about the underlying structure of this data schemas. All I need to do is answer a few very simple questions. Which plant am I looking at? Which products am I interested in, which I've selected here? What are the processes that are associated with the production of this product? And I can also add to this logistics measures and choose some of these attributes. So I can now add some logistics dimensions to my data selection, some operational asset events that are important and relevant to my investigation, for example, maintenance events. So again, I can go through each and every one of these and choose some values and create myself a view of data that has all these dimensions associated with it. So I've already done a lot of the data selection, and what I'll do now is I'll open up the launchers. So launchers, which I'm going into after my data selection, essentially what I'm doing, I'm creating many different permutations of data selection, data manipulations, in order to confirm or disprove my hypothesis regarding the scrap and yield issue of product 4. So what you see here, as I build a new data launcher, is that Analytics for IoT gives me the option to create some very important transformations for different dimensions in the data. For example, transposing the data, fixing periodicity issues, which we can see in the assets. So I can fix my periodicity. I can transpose my tags, and I can choose some some interpolation techniques in there. Um, Default steps. I can fix my events. I can choose some aggregation methods for tags and for events. See that there are a number of methods for aggregating those tags, um, and I can add again. I can add the these dimensions into my data selection. As I said before, there might be different permutations of these data selections. Hence, why I have the ability to create several different launchers within this investigation screen. I can also apply genealogy to the data, which creates a batch subset of the data in reverse and forward order. That becomes very useful when I deal with product batches, which is going to be part of my investigation. Now, in these launchers, what I'm able to do is I may want to tackle the data that I've selected from different aspects, from just exploring the data, so from using familiar tools to engineers, to actually building some advanced code if I'm a data scientist, or exploring and visualizing the data in visual analytics, which is what we're going to do next, or using visual data mining and machine learning, which is our modeling environment. So I'm actually going to go through a number of these. And let's go into visual analytics. So this will take this will take my data selection from before, where I selected the Portland plant, product number 4, and a number of the operational processes involved, and it would bring me straight into the ability to explore and visualize data. Now it's pulling in all the sensor data, all the settings and parameters that were relevant to the processes that I selected before. You can see a lot of that data selection right down here below. So for example, if I select some of these machine parameters and I drag them into my canvas, then visual analytics will, in this case, create a scatter plot to represent the data relationship between these two sensors. So I can see these data points represent relationship between the two. I've actually gone through a lot of this analysis before, so what I'll do is I'll open a scrap analysis that I've prepared before. And the first thing I'm going to see is a frequency of breakdowns associated with a particular set of machines that are linked to product number 4 that I selected to analyze. So these are fault codes that are coming from my MES, and I can see some maintenance-related issues, for example, corrosion, leakage, equipment jammed, which is something that I need to further explore because it's not something that I would typically expect to see in the Portland plant, and I can see how it's affecting the yield of product number 4. We're going to need to see what affects the scrap as well. So one very typical reliability analysis would normally be presented as a waterfall, which again is showing me some further maintenance-related issues that I would need to explore, and where I'd need to go next to understand which machines, which parts in those machines are causing the maintenance issues. That's where I'd like to go next to try and address and try to put prediction systems in place that would help me prevent and avoid these in the future. So I want to see if any of my process parameters within different machines are correlated to one another. I can see correlation matrix here, and I can see some strong correlations between some of these parameters. Another way to evaluate these relationships is to plot these parameters together. So I've plotted them in scatter plots, and I have them um, color coded based on the cost of quality. The high versus low cost of quality, and I also added a filter for high yield and low yield related batches. So if I focus on the low yield, I can see those relationships where the yield is bad, and again I can see some linear relationship here between parameters 39 and 40, so these two sensors. When I drill into this relationship, I can compare it across different assets in my process. So I can see the histograms there, and I can select that for particular assets that I've got running in my plant. And what I'm trying to do is identify if this relationship is behaving differently in different machines in the process. And I am seeing slight differences there in the distributions, and I'm seeing some differences in the relationships. The next tool I'm going to use is an unsupervised machine learning technique and cluster together batches of product 4 that I produced in order to see if there is any common characteristics. So I do have 5 distinct clusters of batches of product 4, and if I wanted, I could focus on individual clusters to try and understand the characteristics of different sensor values in those clusters and look at differences between them. And I can also try to filter down the batches to only look at my low yield batches. So if I take it just about over here, this will filter it down, and I can see that there is one asset that is emerging as a problem asset across all the different batches I'm producing for product number 4 in the Portland factory, and that's this asset number 2210. So next thing I would like to do to investigate this is to look at the production flow between the different stages in my production process. And to do this, I'm looking at a path analysis. So I can see the product flow as it flows through the manufacturing process. And what I can do is I can change this over to my asset codes, and I'll try and see if I can learn anything about the asset that I've looked at before. This should actually show me the flow of product batches throughout my manufacturing process as it flows through these different machines. What I can do is I can trigger this analysis for different batches. I can look at different product batches and understand how different batches have gone through the different stages of the production line. Otherwise, I could actually just filter down all batches and just look at the low yield batches. And again, the same thing happens, so I'm actually seeing that every low yielding batch is flowing through this same asset that I've seen before. PSAA 10, one of my machines. Next thing I can do is start building out some analytics. So looking at a decision tree. What I defined for this decision tree as a target is any batch of product 4 that had over 30% scrap. So I've chosen that as my target for this decision tree. And I explored this with different features and let the tree build out. If I zoom into this tree, you can see that it's using a prediction of a good and bad response graph. So I'm looking for the batch in blue. I'm looking for the bad bad batches, and I can see that again, 2210 is an asset that comes up as a predictor, and that's on my decision tree. And finally, what I'm seeing in the tree is I'm seeing parameter 34. So that's a sensor that is associated to this asset, and it's actually highlighting this as a predictor for bad yield batches for product 4 when the sensor value is under 1351.82. Whenever the sensor value is under this value, it comes up as a predictor for bad batches in this product. So now I have an idea of what I'd like to model and predict. What I would like to do next is compete this decision tree along with other machine learning algorithms and try and find the best performing one. What I'm doing is I'm creating a pipeline. Pipeline is an analytical process. It's primarily for supervised learning. And what this pipeline will do now, it will pull in all the metadata, it will pull in all the data filtering and data preparation that I've done earlier, and also partition the data. It will bring in my decision tree that I interacted with before. And what I'll do to this, once it loads all the project metadata, is I'll start to add some more algorithms to compete with the decision tree. So the algorithms I'll add to it will be a logistic regression and a neural network. And while I run this, I'll talk a little bit more about what this does. Just let this execute. And expand out this menu here on the left. So I want all these three algorithms now to compete based on performance. And what you're seeing here is pipelines allow me to prepare an analytics process with some automated procedures. So I've got an automated feature extraction that I can use, and that uses principal component analysis and robust PCA, SVD, and other techniques. I have anomaly detection that I can drag in, and that uses support vector data description, or SVDD. SVDD works really well for performing condition monitoring and anomaly detection for high-frequency multivariate data. And this works quite well in situations where we're trying to perform condition monitoring in real time, but we don't have historical failure data. So our SVDD will pick up anomalies without the need to learn from historical labeled anomalies. It works really well on data that is not normally distributed as well. There's an automated variable selection to reduce the number of inputs, and it's possible to add open source code nodes with Python code or SAS code to perform any type of action or modeling during the process. So this can be embedded anywhere in the process. So supervised modeling here also comes with auto-tune. I can control the hyperparameters for each one of these models. But the model also has the power to fine-tune the hyperparameters to optimize the performance of the model. And auto-tune really helps drop the misclassification rate. I've got a model comparison here, which I'm going to open up, and this will give me all my assessment data for the three models that I executed. And I also have a pipeline comparison. So pipeline comparison is where I compare between different pipelines. If I built additional pipelines in this project, I can pull in pipelines from colleagues. We do have a pipeline sharing exchange, or you can also use best practice pipelines from a template library. So we have a template library that allows you to pull in different templates and then compete the pipelines for best performance. So an example here, the I bring in a pipeline from my templates, and you can see some advanced and more basic, intermediate templates for different type targets and for different type missions. So this is an extensible library, and normally what we see is we see this getting populated with some best practice pipelines. So predictive maintenance or predicting remaining useful life, performance degradation, stability monitoring type models. This is where these models end up leaving it as templates for people across the organization to use. Let me just cancel this and go back to my pipeline comparison. So what I do want to do next is to productionize the champion model. And the champion model was, in fact, the decision tree between those three models. And I want two things to happen here. One is I'd like to register my champion model into my model manager and also register all the challenger models. And I would like model manager to continue monitoring the performance of my champion model moving forward. I don't want to end up with a model that is underperforming when new data emerges. And I want model manager to help me retrain the model and alert me when a new model needs to be deployed. The second thing I'd like to do is to deploy it back down into the Portland factory itself, where I have an OPC-UA server, which is an industry standard in manufacturing. And that server is acting as a local IoT gateway. It's aggregating machine data from my sensors and parameters coming off the machines in real time. And that's where I would like the inference of this model to actually happen in real time as the data streams through. So I have a few options here. I choose to register the model to Model Manager. This is now collecting all the metadata of this project, and it was successfully registered to the Model Manager. It's possible to also score data directly from here, so it's possible to produce a REST API right from here that could be invoked to score data by an application over API. And it's possible to also produce this code as SAS code or Python code. So that could be scored, that could be invoked as an endpoint through the code, and it will produce the score tables inside CAS. Models can also be published from here into a database, score data as at rest inside CAS or in Hadoop or in Teradata, and CAS actions will do the scoring behind the scenes. Another option I have here is to publish to SAS Micro Analytics Server, which will score real-time batches, so micro analytics service, and the scoring is done using RESTful APIs. So what I'm doing next is going into my model manager. As I said before, model manager will also monitor the performance of my models moving forward, and this is where I can trigger a retraining process whenever model manager identifies that the model performance has degraded, or one of the challenger models has now become a candidate champion. I'll go into this project and choose my model. I can have the model I want to promote as a champion. So now this will be published by model manager as a champion model. So I'll consume this within SAS event stream processing. That's the next step I'm going to in order to productionize this model and have it executing in real time. You can see some of the metadata that was captured here, variables, properties, scoring code, and under performance is where I can build my performance jobs that will be monitoring performance on an ongoing basis. So they will produce performance reports, and once they alert me that there is performance degradation, I can actually trigger off the retraining right from here. So if I trigger off retraining from within a job in Model Manager, it will go and re-execute the pipelines we've seen before, and it will also impact the deployment inside SaaS event stream processing, which is the next step in the process. So it will automatically alert the deployment mechanism that a new model has now become a champion model. So let's go and register this model in event stream processing. And again, I'll just say that with event stream processing, what I'm going to do next is I'm trying to build a pipeline that will process the data in real time and then push that inference down to the edge gateway in the factory in order for it to score live streaming data against the model, and then also potentially actuate in my manufacturing process to prevent product force scrap and low yield from happening in the future. So I'm now inside Event Stream Processing Studio, and this is a design time. So this is where I build all the real-time data pre-processing, the model scoring. I already have a project which I started working on here. And this is where I defined also all the actions that I would like to take in order to deploy on stream of data that my plant is producing. So I can deploy this stream wherever data and action need to come together. It could be in the cloud, it could be on premise, off-premise, data center, or it could be the edge gateway. And in my case, it makes sense for me to eventually deploy this on the edge device sitting in my factory because of the latency requirement. So I really want to take immediate action when there's any scrap coming off the problematic machines for the product that I'm predicting for. So I already started building out this project. I just dragged in these nodes, we call them windows, and I added a source window, which allows me to define what I want the data input schema to be. So I've got an input schema, and I've got my publisher or connector. These are connectors that are built into this window, and there are many more. So we have over 300 different endpoints that we can connect to, but you can see that within this source window, I have an OPC UA connector, I have a WebSocket connector, I can connect to IoT data over MQTT or AMQP, over RESTful APIs, JSON. I can go and grab data from my edge gateway in many different ways. And to continue this flow, I'll add to it a copy window. So a copy window allows me to define retention periods. So I can now hold data and events in memory. I can hold, let's say, the last 5 minutes of data and then calculate moving averages or standard deviations on moving time windows within this node. And these are all calculations that are built into these windows. So I don't need to code any of them. They're built into it. What I'd like to do next is add my champion model, which will be pulled in directly from Model Manager. So I'll pull in a calculate window. And I now have a calculate window, and I'll just change the settings to a user-specified model. and import my model from Model Manager. So this is now going into Model Manager. This could be a long list of different projects, and you can have different models from different projects working within different calculate nodes in the same project flow to perform different actions. And this will now pull in the entire definition of that predictive model I've built before, and also pull in the output schema into this window. And this would allow me to basically define moving windows of time periods coming off my publisher, my OPC UA server in the factory, and have that data streaming through a continuous query of my predictive model. This predictive model is right here, and the next step for me to do is to actually test this model with test data or deploy it to a test OPC UA gateway to make sure that it's not breaking anything in the production process. And then after that, I would use our deployment tool in SAS Event Stream Processing, it's called Event Stream Manager, to then push this project to the execution runtime container that is installed in the factory. So in the interest of time, I won't be going through that technical flow in this webinar, but what I did want to do from here is talk to you about a use case of one of our customers called Lockheed Martin. So this is my last slide, and Lockheed Martin is a customer that we're very proud to partner with. It's of course a very well-known aerospace company, and they're also the original equipment manufacturer for the C-130 models and the C-130J models, which are better known as Hercules. These C-130J airplanes, they contain around 600 sensors. They're located throughout the aircraft, and they produce about 72,000 rows of data per flight hour, every flight hour. So very critically, this data includes fault codes on failing parts. Previously, this IoT data, which streams from the aircraft to the facility that houses it, was stored in different disparate data systems. There was no central repository for more than 400 of these aircrafts that were operating in different countries around the world. So effectively, that left engineers at customer sites on their own to maintain the aircraft based on their interpretation of the data, and very often leading to unnecessary maintenance and multiple days of downtime while parts were being shipped from faraway places. So using SAS, Lockheed Martin launched a service called Intelligent Diagnostics, which cleans and stores the data in a consistent, repeatable, and scalable way, as we've seen before. And for each aircraft, it takes into account all the historical maintenance that was done on it and integrates that with the fault and sensor data that comes off the aircraft while the moment the aircraft lands. And it does all those calculations in stream, as we've seen before, and it delivers that diagnostic intelligence to the engineers in whatever facility they're in, advising them what they need to go and fix. And you can see an example for a bottom line saving there. So they reduced 1,400 hours of downtime of the C-130Js in a 3-month time window. And it's a great example of how AI and IoT, they not only deliver efficiencies, but they also help transform a business model and generate more revenue through servitization. So we're coming up to 10 minutes before the hour, and this has been the last of my slides, and I believe that we have some time left for some Q&A. Julie?
Thank you, Kevin. Yes, we do have time for Q&A. We've got some questions that have come in already, and I would encourage any of you who have any other questions to go ahead and send those over now. But let's get started with our first question. Is there a list of IoT devices that you integrate with?
Yes, well, so that's a very common question. So what we've done in designing our software is to invest as much as possible in building connectors and adapters and invest in our publish and subscribe API, which means that any system can be connected to. So this really applies mostly to ESP as a data ingestion engine and subscriber. And I mentioned before, we currently support over 300 endpoints, from connectors to systems, databases, historians, to open source systems like Cassandra, Kafka, RabbitMQ, Camel, and some standard connectors like MQTT, OPC UA, HTTP RESTful, WebSockets, etc. Part of our IoT go-to-market strategy is to partner with device manufacturers, and they have libraries of drivers that are built for specific data sources. For example, OEM machines in multiple industries, controllers, PLCs, SCADA systems. So that kind of integration is always going to be part of an IoT project anyway, and controllers are notorious for having proprietary software in them, but there is now a growing number of providers in the IoT market that have IoT gateways with connectivity out of the box, and they publish over a standard like MQTT, OPC UA, or AMQP, which we subscribe to very easily from the ESP Studio interface. So, so in short, we don't offer the hardware, and we don't feel like we need to certify any hardware necessarily. But what we do have are hardware and software minimal requirements in our documentations. If you follow the link that is on the screen right now, you'll be taken to some of these technical requirements. And we deploy the ESP for the edge device on a Docker container running Linux, and we have recommendations of how to size that. So even if we don't certify devices for integration, we've generalized to be able to work with pretty much any device that is running Linux in it.
Okay, it helps you to hear me when I'm not muted. So realized I was talking for a minute on mute. How do you integrate with public cloud providers?
Okay, so we continuously work in collaboration with the large public cloud providers I mentioned before, and we work with them to create tighter integrations to their IoT platform services. At the moment, when you deploy analytics for IoT on Azure or AWS, you get the benefits of SaaS Via being architected for cloud deployment. So if you're on Azure, you can manage it from your Azure portal. You can scale the amount of CAS worker nodes required to perform tasks elastically, and all the other cloud functionality that we now have in Via. Just last month, we announced a partnership with Siemens MindSphere, which is a very popular industrial IoT platform, and that runs both on AWS and Azure. And we announced that there will be a number of components of analytics for IoT rolling out over time onto MindSphere, embedded as a fully integrated platform service, with the first service being ESP Server and ESP Studio that we've just gone through, and that's coming this September. So, so we have several ways of working on the cloud with the public cloud providers, and we're also collaborating directly with them.
All right, I've got a couple more questions here for you. As a reminder, we still have time, I think, for a couple more after these. So if you would like to get your questions in, now's the time to do it. Next question, can you elaborate on how the model executes on the edge without any network?
Right, yes. So I mentioned that before. So the ESP Edge deployment is a small Docker container for a Linux operating system. it executes the project that was designed in ESP Studio, and whether that was done in the cloud or on premise, and pulled in the models we've deployed onto Model Manager. Once Event Stream Manager deployed on the project to the container, it executes all the logic as a local continuous query. So, meaning it will subscribe to the data source locally, assuming there's no requirement in the project to connect to any external enterprise systems. So in the example before, we had all the machine data of the Portland factory connected, aggregating through an OPC UA server, and so ESP would continuously manage data in memory from a data retention perspective and execute algorithms also in memory inside that Docker container on that box. So assuming there's local actuation, it will also launch any automation tasks it was designed to perform, like alarms or alerts or notifications that could be triggered from that same ESP flow that I started building out before. The other thing it could do is it could do some closed-loop automation. So we've had some environments in which they wanted to actuate back into the factory when we're dealing with product quality issues. We can do real-time detection of low-quality products and then actuate back to the controller and say this is a reject. So as the product flows through the machine, it could actually reject it based on some predictive modeling and also deep learning models that we've developed and deployed exactly in the same place. I'll just say that there's also built-in algorithms in ESP in case we are working completely disconnected from the network, so we're not sending the model performance and analytics outputs back into Model Manager. We're disconnected. These algorithms were written specifically for ESP to execute as streaming models. So some of these can also retrain in-stream on the data in motion, things like clustering, regression models. This will retrain the model coefficients continuously. And models don't need the full environment to retrain. We've seen some very secured and locked down facilities where the data can only transfer to storage physically. And in some situations, that was how retraining was done, physically bring back a retrained model or a new ESP project back to the edge device as part of a change management process. But certainly this is emerging as a deployment design paradigm to be more secure, to leave the edge device, which is an IT device, connected to the OT network, but disconnected from the internet, disconnected from the cloud, bring all the functionality and inference back down into that edge device. And that means that some of these machines are built to work for 20 or 30 years, and you need the same type of rigor and robustness and stability from your analytics engine. That's what we're building into ESP, and that's why we've built it into the edge as an independent edge product that can go live in completely disconnected environments. Long-winded answer.
All right, final question here. Can you elaborate on the model building algorithm or method without labeled failure results?
Yes, so I did mention SVDD. So SVDD is one of the techniques that we use in our pipelines, in our data mining tool for performing anomaly detection. So support vector data description, you can see it on our documentation website, is very well documented with some IoT examples that we've provided. It's a really good model for performing condition monitoring and anomaly detection. And as I said before, we've been in situations where we needed to perform this type of condition monitoring or predictive maintenance projects, and there was just no historical labeled failure data for the asset. So really all we were working based on was the actual data that was coming off the pump in one of the examples, or engines is one of the other examples. I think both examples are documented. So we used SVDD. It's a great technique for identifying these anomalies without having to define what are anomalies in the data, or find some labeled failures in the past. See some examples for that, and I'll just mention that we've built SVDD both for the pipelines that you've seen me building out, and it's also a built-in algorithm inside the ESP Studio. So there's a window for that, and that could be performing SVDD live on data in motion inside the ESP project, and that could go live in the on the edge device on the edge, and continuously look for some anomalies in the data.
All right. Before we conclude, I wanted to go ahead and thank Kevin. Thank you so much. We appreciate you